All right, this will be a walkthrough of section 5.2, a little bit of review of bending stress that we've calculated before in strength of materials, F sub B, and then a movement towards plastic moment capacity, okay? So again, the bending stress, bending stress we've dealt with has always been in the elastic region, okay, and we're moving towards the plastic or the inelastic region. Plastic, all right, the plastic or the plastic and inelastic, same terms. Okay, so bending stress was, when we taught in strength of materials, my divided by I. And if I set my bending stress to some allowable, capital F, I could calculate my moment strength as M equals FB times I divided by Y. And, recall that this expression could be S sub X, section modulus, okay? But this is what we refer to as the elastic moment strength. Okay, elastic moment strength. But now we're going to the plastic, okay? And plastic is really sets the strength of the entire cross-section to F sub Y, right? If you think back to this equation, and we'll see this in the presentation, the bending stress distributed like this, right? The only F max would be at the top or bottom, and if we set that to F sub Y, the very top and very bottom would be at F sub Y, but nothing else, okay? So plastic moment capacity takes the entire cross-section and lets it get into F sub Y. So when we think M plastic, it's going to be a different property, right? It's going to be ZX times FY, okay? Here, right, if we set FB equal to F sub Y, you would have, or FB times S sub X, the allowable bending stress, even if it's F sub Y, is multiplied by S sub X. So S sub X is the elastic section modulus. Z sub X is the plastic section modulus. So we'll see that over and over. All right. So again, a lot of review through this section. Again, hopefully this is not new for you. My area times my Y bar equals the summation of, all right, my each individual area times my each individual YI or Y bar to that each individual section, okay? Again, this was all from statics, the end of statics, beginning of strength of materials, moment of inertia, parallel axis theorem, right? The summation of, summation of IX plus ADY squared, okay? Again, you really need to be able to do those pretty efficiently, okay? And we'll talk about plastic moment capacity and how plastic hinges, again, synonyms for each other. So plastic moment, plastic hinge, same type of thing, okay? Again, cross section, all right, S sub X. This is the elastic section modulus. Elastic section modulus, and Z is the plastic section modulus. Okay, so we want to review those, and we'll do examples independent of this lecture so it doesn't get too long, right? So again, we start in the elastic region, and that's this formula. This is the elastic bending stress formula. And again, this is the top, right? The stress distribution. If I have a beam, all right, here's my Y flange beam, has an internal moment m, has a neutral axis. The bending stress distribution is going to look like this, right? It's going to give me compression on the top, tension on the bottom. Okay, so here's my moment. Y is the distance up or down to the point of interest. So if I want to calculate the bending stress right here, I find that distance y, multiply it by my moment, and divide it by Ix. So elastic moment stopped whenever one of these fibers, the very top or the very bottom, when one of these fibers, depending on if it's symmetrical, they reach it at the same time. If it's unsymmetrical, the fiber furthest from the neutral axis reaches maximum stress first. But we could set this equal to F sub y. Okay, so if that's F sub y, then we know that our moment, elastic moment capacity, again is going to be M equals F sub B times I. All right, F sub B times Ix divided by Y. That will be our moment capacity. And if we set this equal to F sub Y, that's then our elastic moment capacity. And remember that Ix over Y was the section modulus. Okay, so again, it's in the elastic region. We have small deformations, so small angle theory, and actually stress is less than or equal to. So F sub B is less than or equal to F sub Y, and again, F sub Y and the proportional limit in our world are the same. Okay, so talk a little bit of theory and how we have these develop these equations in the steel manual. When we talk about bending, the most typical loading condition it's used is two equal concentrated loads symmetrically placed from the ends, so equal distance. So that makes this equal to L minus 2A, right? This being L. And what's nice about this, in this region here, moment is constant. It doesn't change. Okay? Moment has a constant value. And if I take a little deviation back to statics, all right? So if I have concentrated load P, and this would be the last slide in your handouts if you want to go there and follow along. This is our distance A in A. All right, and we certainly have this span L and spacing L minus 2A. But with this two equal loads equally spaced, hopefully we are good with saying this reaction is P and this reaction is P. So now if I plot my shear diagram, right, again, kips and X is in feet. If I plot my shear diagram, I go up a value of P. I have no distributed load, so I have no slope. I hit a value of P down, so I go back to 0. Then again, distributed load is 0, so I have no slope, so I continue across. I hit this concentrated load P, come down, and then I have distributed load is 0, so constant, and then I hit this P and I'm back up. Okay, so that's the shear diagram for our lab loading, so to speak. And then our moment diagram, again, kip feet, X is feet, right? And this is positive shear, so we're going to have change in moment is positive, and it's constant magnitude, so this is constant slope equal to P over 1. So, and then this area, all right, oops, this area here under the shear diagram is equal to the change in moment. All right, and that means that change in moment equals P times A. So this goes from 0, so it's a pin support, to P times A. And then here shear is 0, so it has a constant moment capacity. And then we have negative shear, and then we have negative change in moment equal to the same, and it drops back down to 0. So that's nice, because if we have, golly, we have this region with constant moment. Okay, and that's what we use for a lot of our development of equations. Okay, so here's our force P, RA equals P, shear equals 0, moment equals, again in this region, P times A. Okay, so there's our, we got compression on the top, tension on the bottom. So this is again my max, or C over I. So this is MC over I. Oops, sorry, not that. This stress here is my over I. All right, if I was going to here or here, right, this would be FB is MC over I. Same format, but now it's just, the value of C, the max value. But anywhere in between, my over I, when y is 0, stress is 0. When y is C, stress is max. In between, it's a linear relationship. Okay. So again, we're going to start with a small moment applied, right? And we still have FB is my over I. So with a small moment, right, we're I'm not sure how that got in there. Yeah, that comes out. Small moment, then FB is less than FY, right, or FB max, I could call it. Okay. Then as I increase the moment, eventually I get to the elastic moment, where FB max hits FY. All right, so both here, we're assuming a symmetrical shape, and here are at yield. And this would be the elastic moment capacity, or strength. Okay, but we still have more material, right? All this material in here, all of this material still has more strength left. It's not reached F sub Y. So we have more moment capacity. Okay, we have more moment capacity. And as we increase our moment, again, this Fy is the maximum limit, right? Remember, because when we talk about stress versus strain, we have the straight line portion, and we have the elastic region, or the plastic region. This is Fy, this is elastic, this is the plastic, or inelastic. The inelastic region. Okay, so as soon as we hit Fy, that material is spent. There's nothing more for it to contribute to the system. But all of this material in here has more capacity. So we can increase the moment, but the outer fiber stays the same. The stress of Fy just propagates down into the section and up into the section. Then eventually the entire cross section is at Fy compression, Fy in tension. And that moment is referred to as the plastic moment, and it's this property Zx times Fy versus S sub x. Okay, so again, elastic moment capacity, M elastic, is going to be Fy times S sub x. Okay, this is my plastic moment capacity. Is going to be Zx times Fy. So we have to talk about Zx and how to calculate that. Okay, distinctly different than S sub x. But now this is referred to as a plastic hinge. All right, the entire top half is in compression at Fy. The entire bottom half is in tension at Fy. Okay, plastic hinge. All right, so there's our plastic hinge. So there's no more moment strength there. Notice too here, the moment capacity here is 0, right? M cap, or the ability, I should say, is there's no moment here. This has to be M equals 0. This has to be M equals 0. It's a ruler. This is a pin. So they essentially act like a hinge, right? So, think of, something that had 3 hinges, and there's 1, 2, 3. This beam is on its way to collapse because it has no more bending capacity. Okay, if we were to change this situation to be fixed, all right, and then roller over here, when this hinge develops, it's still stable, right? When the plastic hinge develops here, it's still stable because we have that fixed end. Okay, and remember, before I applied that plastic hinge, right, when it was just this beam here, this was 1 degree indeterminate, right? So it had an extra degree of determinacy. When we put that hinge in there, that takes away that extra variable. Okay, so if this were an indeterminate problem to begin with and we developed one more hinge, notice we'd only have 2 hinges. So this has more capacity, but again, as soon as this over here reaches a plastic hinge, then we're done. Okay, so it's really like when there's 3 hinges in a beam, we have a problem. Okay, so plastic neutral axis, also you'll see it referred to as the PNA. The plastic neutral axis is the location where all half the area is above, because the entire area goes into Fy, and half the area is below. And we have equilibrium, right? We have compression area, inches squared, times kips per inch squared. And we have tensile area, inches squared, times kips per inch squared. So this section is in equilibrium. And notice it's separated by distance A. And really what C and T are is really the centroid of this shape above and the centroid of this shape below. So the entire area, all right, so you get the entire area is going to be A sub C, and then multiply by Fy, okay, and bottom half, you get the entire area in its centroid, and that's going to be my A sub t times Fy. And so this distance here is really A. And we'll do some examples to show you how to calculate that. But another way of thinking about it, maybe a little easier, since you have these two sections, the top flange and the top half of the web, is you could separate it into two separate forces. Okay, but I got a little ahead of myself. Let me, just go back or finish out this thought. Okay, so A over 2, right? This is AC equals AT, okay, equals A over 2, times this moment arm, right? This is my moment arm. It's a distance between two forces, two equal and opposite forces. So this whole product here is Z, in this case Z, we'll just call it Z, but if we're bending about the x-axis, it's ZX. So Z equals, in this case, A over 2. That's easy. Now getting this moment arm, that's the challenge. Okay, and there's a couple different ways. We can do it this way, right? We can break this up into two elements, or two parts, the top half, and then we could break it into the the bottom half. Okay, and find those areas, and again find the location to the centroid. This has a centroid, and this has a centroid. This could be like y to the top. This could be y to the bottom. If they're symmetrical, they're the same. This entire distance is what this A value is. Okay, and the moment would be A times half the area times F sub y. Okay. You could also break it up into, 4 elements essentially, right? We could break it up into the top flange. Oops. We could break it up into the top flange, the web of the top flange, the bottom flange, and then the web contributing to the bottom flange. That might be a little quicker, a little easier. So now you have this centroid, you have this centroid and its moment arm, this centroid and its moment arm, this centroid, and finally this centroid. If you sum those moments, you also get M sub P. Okay, so this would be compression in the flange, compression in the web, tension in the web, and then tension in the flange. Okay, they all would add up if you sum moments, right, to get the plastic moment. All right, so we'll do some examples. I'll get those posted, but that's kind of the end of this section. Again, feel free to contact me with questions. All right.